In this video, I'm going to talk about electric fields and parallel plates, and I'm going to use a couple of online simulators to help demonstrate the concept. So I'm going to start with this one of a simple circuit, which hopefully is familiar to you. You've got a battery or voltage supply. We've got some sort of load. In this case, I'm just using a resistor, but I could use a light bulb to demonstrate it. And I've put in an ammeter to measure the current that's going through the circuit. I've got a switch to open and close it, and I've got a voltmeter to be able to measure the voltage across the load. So it'll be a good opportunity to also talk about concepts like electron flow versus conventional current. So in physics, we tend to more talk about the conventional current, but just to know that electron flow will be in the opposite direction to conventional current, and I'll talk about that in a sec. So I might show current as in terms of conventional current, firstly closing the circuit, and it will show you that conventional current goes from the positive terminal of the battery through the circuit to the negative terminal. If I turn on electron flow, you'll see that the electrons actually flow through the circuit from the negative terminal of the battery to the positive terminal. So I'm going to keep it set to this because this will be more useful when we're looking at what's going on when we're charging up these parallel plates. So we'll just come back to the battery here. I've got a 1.5 volt battery connected. So that's our supply voltage, or we can think of it as a voltage gain in the circuit. If I connect the voltmeter, now the voltmeter needs to be connected parallel, so that means it has to go across. So you don't put this in series like the ammeter, you have to measure the voltage across the load. What you'll see here is that our supply voltage is 1.5 volt and the voltage across the resistor or the load is 1.5 volts. But we actually refer to that as a voltage drop. So we've got a voltage gain of 1.5 volt and a voltage drop across the load of 1.5. Okay, so that's the basics there. Let's go back to this simulation and have a look at what's going on here. So one of the big differences you'll notice here is this gap. This is not a complete circuit. There's a gap and it's filled with air. And the air is acting, I guess, like an insulator so that it's going to stop current from flowing. So electrons are not going to jump across this gap. So what's going to happen? We'll have a look in a sec. I'm put that here. Okay, so I'm going to increase the voltage of the battery. So I'm going to just take it up a little bit and watch what happens. It's not going to show the electron flow like so, but it will show flow in terms of an arrow. So, okay, so I'm going to increase it to 1.5 volt. So if I increase this, look at the arrow, but I stop increasing it, the arrow disappears. All right, so I'll take it all the way up. So it's at 1.5 on the supply voltage, but this arrow is stopped again. So what's going on here? I'll take it back down a bit. Watch what happens. So we had this arrow is representing the direction the electrons are flowing. Okay, so have a look at what's going on. We've got on these two plates. So if I take this voltage down, notice the arrow's going the other way. Okay, so now I'm going to connect the voltmeter to one to each terminal. So if you watch what's going on with the voltage here as I increase this. Okay, so firstly you should notice that the plate connected to the positive terminal of the battery becomes positively charged, and the plate connected to the negative terminal becomes negatively charged. This is because, if you noticed, the electrons were flowing in this direction. So they're leaving this plate and transferring to this plate. And as you notice with the voltmeter, as the supply voltage was increased, the voltage across the plates was increasing. So you should notice that as the supply voltage increased, the voltage across the plates increased. And once the voltage across the plates equals the supply voltage, the flow of electrons stop because the plates are fully charged. And what you'll notice is that the charges spread out evenly over the plates. And the other thing is that because of the gap, acting like an insulator, the electrons won't jump across. So you've now got what we call a potential difference. So we've got a high potential and a low potential. And because you've got this potential difference, we've got an electric field. And we know that the electric field goes from positive to negative. The directions, by definition, the direction that if you put a positive charge in that field, it's the direction that that positive charge would move. So the positive charge would move towards a negative plate. And a negative charge, such as an electron, if placed in that field, would move towards the positive plate. So there's a force that acts on the charges that you put in that field. Right? And you've got a force, it's a net force. It's going to accelerate according to F equals ma in that direction. So even if you turn off, the simulator's not going to work the same, but well, actually, let's try it. If I disconnect the battery now, the plates will stay charged for some time. Eventually, they'll slowly, the electrons will leak away, but they'll stay charged for quite a bit. We can use this simulator to also measure the electric field strength between the plates. So with the formula E equals V over D, so the V's the potential difference across the plates, or the voltage across the plates, and the D is the distance between the plates. So this is his separation. And then once we've found the electric field strength, we can use the formula to work out what the force would be on a charge placed within that field, using F equals QE. So just to recap, we've got our supply voltage here. We've got our parallel plates. We've got this space or a gap between the plates, which is an insulator. We've got our plate separation, which is D. It's in millimeters, but we like to measure it in meters. So when we turn on the power supply to 1.5 volts, for example, the electrons are going to transfer from the positive plate. So we'll call that electron transfer in this direction, and they're going to transfer to the bottom plate. So this one becomes positively charged, this one becomes negatively charged, and the current will flow, or the electrons will stop flowing once the voltage across the plates equals the supply voltage. So we'll call this voltage across the plates. So now you've got this potential difference between the plates. You've got an electric field, which we give the symbol E, and the strength is dependent on the voltage. The strength is dependent upon the voltage and on the separation between the plates. So if we put a positive charge inside that field, we know it's going to experience a force downwards. It's going to accelerate it downwards. If we have a negative charge that we place in there, it's going to experience a force upwards against the direction of the electric field. So the positive moves in the same direction as the electric field, negative moves in the opposite direction. So we've got our formulas that we'll look at. The strength of the electric field is that, and then the force experienced by the charge within the electric field is given by this. So if we know this value here, we can then substitute it into that. If we know the charge, we can calculate the force acting on the charge. Now, before we go on, I just thought it'd be useful for us to compare an electric field with a gravitational field and the effect of a gravitational field on a mass within that field. So this is a mass, and say we've got a positive charge and a negative charge within the electric field. The gravitational field has a strength of G of 9.8 newtons per kilogram, but we also use the unit meters per second squared. Okay, so we know there's a force that acts on the mass in that field, within the gravitational field, in the same direction as the field, and it's directed towards the center of the Earth. So the force, we'll say due to the gravitational field, is the mass times the gravitational field strength. You've got a positive charge in an electric field. So we've got an electric field, and you've got a charge. Now this is a positive charge, and then you've got a negative charge. So the positive charge is going to experience a force towards the negative plate, and the negative charge is going to experience a force in the opposite direction. And the formula for calculating the force, and we'll say due to the electric field, is equal to the charge times the electric field strength. And we know we can calculate the electric field strength if we know the distance between the plates and if we know the voltage across the plates, and then we can calculate using that. You can substitute this into this equation here, so you'd end up with Q times V over D. So it gives you an equivalent value to that one. So we can see how this formula is related to our Newton's second law equation, F equals ma. But the same as this one, we've also got, this would also equal to mass times acceleration. So let's now look at a problem. So I'm just going to do this as an open problem. Here's some details about parallel plates with an electron placed at one end and you've got a supply voltage of 200 volts and a distance between the plates of 5 centimeters. So what can we get from this this setup? What calculations can we do? Well, firstly, we know the supply voltage, and we know the distance between the plates is 5 centimeters, but I want to convert that, so I divide it by 100 to get that value in meters. So if I know the voltage and I know the distance between the plates, I can calculate the electric field strength using this formula. So it's simply 200 volts divided by 0.05 meters, and I can see what units I'm going to get, and you can work out in your head that calculation should be 4,000 volts per meter. Okay, so what information is not provided is the charge on the electron. So we get that from the syllabus data sheet, which gives a value for the charge on electron as minus 1.602 times 10 to the minus 19 coulombs. Okay, so I know now my electric field strength. I know the charge of an electron. I can calculate now the force that's going to act on that charge using this equation here. So it's a matter of substituting in this value. Okay, now the units we've got here is volts per meter. A quick look at rearranging this equation tells us that we have an equivalent unit of newtons per coulomb. So I can change this, so it's saying that 1 volt per meter is equivalent to 1 newton per coulomb. All right, so then I can cancel out my coulombs and I'm left with Newton's force, which is what I'm after. So I wouldn't expect you to be able to calculate that in your head, but you should get something like a negative value, 6.4, 10 to the minus 16 newtons. Okay, this negative value gives you direction because a force is a vector and it's saying it's going to be in the opposite direction to the electric field. So which direction is the electric field going? We should probably draw it in. We've got positive, so this is a positive plate, this is a negative plate. The electric field goes this way. So the force on the electron is going to go in the opposite direction. So it's going to go in this direction. So the force on the electron. Well, now that we know we've got a force acting on the electron, I want to know what's its acceleration. I can say that this electric field force is equivalent to the net force, and which equals mass times acceleration. So I can just substitute this value as in my net force, and I can get the mass of an electron also in the data sheet, which is given as 9.109 times 10 to the minus 31 kilogram. And I can substitute that into this equation, rearrange it to get the acceleration. So I have minus 6.4 times 10 to the minus 16 newtons equals my mass, 9.109 times 10 to the minus 31 kilogram times acceleration. Okay, so that means I have to divide this value by this value, which gives me negative 7.03 times 10 to the 14, that will give me newtons per kilogram, which I know is the equivalent unit to meters per second squared, so for acceleration. The negative also indicates that this force is causing the particle to accelerate in the same direction at that rate. Okay, I think that will do.